Hello friends, welcome back to my YouTube channel. In this video, I'll be continuing my discussion on tall columns. This is part 7 of my discussion, and today I'll be talking about uh, analysis of stresses induced in the wall of a tall column. Again, this is a continuation. For a few past videos, I have been discussing this analysis. Now, up to part 6, I have completed discussing all types of loads, that is stresses that are induced due to different types of loads. So in this particular video, in part number 7, I'll be talking about stresses that are induced due to all types of loads. So whatever important loads to which a typical tall column will be subjected, all type of loads will be now considered as stresses due to those loads will be considered in this particular discussion. In my earlier videos, I have discussed each load separately. You can please refer those videos. You can watch those videos. I'm going to give links to those videos in the description section. So first task in this video is to consider all the stresses, or rather to consider stresses due to all types of loads. And the second task in today's discussion is what are the design considerations for tall columns. So based on all the stresses, what are the design considerations, that also I'm going to discuss. So in short, we can say that you can say that I'll be talking about the total stress, which is simply addition, you can say summation of all stresses due to all types of loads. Okay, so let us begin the discussion. So first, we will know what are the loads that are responsible for inducing stresses. So first you have internal pressure, external pressure, or vacuum. So these are going to induce longitudinal stresses, that is stress in axial direction. This is one thing. Plus these are also going to induce circumferential stress, which we also call it as hoop stress. What is the nature of these stresses? They will be tensile and compressive. So due to internal pressure within the column, or due to external pressure or vacuum, you have axial stresses, you have circumferential stresses that are induced, and their nature is tensile and compressive. Then dead loads are also responsible for stresses in the wall. These are longitudinal stresses, that is axial stresses, and their nature will be compressive. These stresses will be compressive. Wind loads also induce longitudinal stresses. They may be tensile and compressive. Eccentric loads also induce longitudinal or axial stresses, and they are responsible for producing bending stresses. Seismic loads, these produce longitudinal stresses. They may be tensile and uh, compressive. Okay. So in my previous videos, I have covered all this. Now over here, we will consider effect of all these stresses and how to consider that in the design of a tall column. ठीक है. So first, I'll be summarizing the equations. So for internal pressure, the circumferential stress or hoop stress that is induced due to internal pressure is given by this equation. Fc is equal to di into p upon 2 into ts. Whereas longitudinal stress induced due to internal pressure, it is given by this equation. Fa is equal to p into di upon 4 into ts. So internal pressure is responsible for two types of stresses. First is circumferential or hoop stress, and that is given, this stress is given by this equation. And second one is longitudinal or axial stress, and this is given by this equation. Fa is equal to p into di upon 4 into ts. Then external pressure or vacuum. Under the influence of this two, you have circumferential stress or hoop stress, and in this case it is given as Fc is equal to dO into P upon 2 into Ts. Now in this equation, the internal diameter is replaced with outer diameter. Similarly, longitudinal or axial stress will be given by this equation. Fa is equal to P into dO divided by 4 into Ts. Again, you can check the internal diameter is replaced with the outer diameter. What are the terms involved? Di is internal diameter, P is pressure acting. It may be internal pressure or external pressure. Then Ts is thickness of the shell of the column, and dO is outer diameter. When you talk about dO, then that dO, if it is an insulated column, dO will also include diameter of the insulation. So you have to take care if you are analyzing stresses due to external pressure, and when you consider dO, and if the column is an insulated column, dO will include the diameter of the insulation as well. So in case of insulated columns, dO includes diameter of the insulation. Okay. So now due to internal pressure, how to calculate the stresses? You have these equations. Due to external pressure or vacuum, how to calculate them? You have these equations. So the point to remember is, due to internal pressure, you will have circumferential stress and axial stress, and same is the case with external pressure or vacuum. Okay. Then let us now know what are the stresses due to various dead loads. So for that, I am showing a simple schematic of the column, insulated column. So this is outer diameter of the column, this is diameter of the insulation. So these represent insulation. Now we are going to consider a distance of x from the top of the cell for our analysis. So now let us know what are different dead loads. First is weight of the shell. So I have already discussed it in a separate video. I'm going to give link to that video in the description section. So weight of the shell. What is the stress? How to get stress that will be induced due to weight of the cell? Let us understand. So that is given as FCS is equal to x into rho s into g. So x is the distance that we have considered from the top of the shell. Now within this distance, the thickness of the shell is uniform. The distance is to be selected in such a way that thickness is uniform. So for that distance or weight of the shell up to this distance, that induces a stress that is given by this equation. FCS is equal to X into rho S into G, where you know rho S is density of the shell material, G is acceleration due to gravity, and X you already know what is that. Then other dead load that comes into picture is weight of insulation, and for that the stress induced due to weight of insulation is given by this equation. So it is din square minus do square into x into rho in into g divided by 4 into di plus ts into ts. Din is the insulation diameter, you can see over here. Do is the outer diameter of the shell. So di is internal diameter of the shell, ts is shell thickness, rho n is density of the insulating material. Other terms they are shown in this diagram. So Tn, as I said, this is insulation diameter. Do is outer diameter of the shell. Okay, so due to weight of shell you have this stress. Due to weight of insulation you have this stress. This is dead load number 1. This is dead load number 2. Okay, now let us continue the discussion. The other dead load that you have to consider is weight of the liquid. So for that, let us understand the concept. So I'm showing a tray over here. Then this will be the outlet weir for that tray, and this will be the downcomer. And liquid, let us say a height of the outlet weir is HW, and now you have tray, you have liquid on the tray, and we are concerned about weight of this liquid. So for calculating stress due to weight of liquid, first we should know how to calculate this weight. So let us understand that. Then this distance, let us denote it as HD, the distance of, or you can say the opening of the weir. That distance is HD. Again, one more thing that we will be considering is the distance. This is called top disengaging space. So this in this column, this is the topmost tray. Above this tray there is a certain space provided, and we are calling that as top disengaging space. And let this length, that means length from the tray to the top of the shell, be LD. So all these parameters will have to be considered for calculating stress that will be induced due to weight of the liquid. So the stress is given by this equation. I have discussed it in a separate video. You please watch that. So I'm just showing you the equation over here. So this is FCL is equal to X minus LD divided by S plus 1 into pi by 4 into di square minus HD square into HW into rho L divided by pi into di plus TS into TS. Now in order to understand some concepts over here, let me show you a tray. Now I am showing you a tray, and this is the weir. Okay, so the point is liquid will be lying in this area. On this particular tray, liquid will be occupying this space, whereas this being weir, the liquid is going to go through this weir to the bottom tray. Okay, so this is the tray. You have the downcomers. You have the downcomer, the diameter, internal diameter of the column, that will be equal to diameter of the tray, and this is the distance, you can say diameter of the downcomer. If you have this type of downcomer, a circular pipe, this is one of the design. ठीक है. So for that circular downcomer, let HD be, HD shown over here is nothing but diameter of such a downcomer. Then is you may have another tray, another type of tray, for example, where some portion of the tray itself is used as the downcomer. So let us say that this is 75% cut tray. That means 75% of the total area will be the tray part, whereas the remaining 25% will be the downcomer area. So liquid will be going to the bottom tray through this. Okay, then diameter is di. In this case, you can calculate the tray area by using this equation. So this 80 will be 0.75 into pi by 4 di square. That is, tray area will be 75% of this area. In this case, how to get the area that will be available for holding the tray? It will be given by this formula. So this pi by 4 di square, that means this total area, minus pi by 4 HD square, this area. So total area of the tray minus area occupied by the downcomer will give you area that will be available for the liquid. Okay, so for this particular tray, in this equation is applicable when you have this type of tray. For this type of tray, the only thing that will be changing is the area. So instead of pi by 4 into di square minus HD square, it will be 0.75 depending on the percentage cut of the tray. This will be 0.75 into pi by 4 into di square, for example, in this case. Okay. So in this way, you have to calculate, or you can calculate stress that is induced due to weight of the liquid. So in this equation, S is the tray spacing, di is internal diameter, ts is thickness, and rho L is density of the liquid. All other terms are clear. They like HW, HD I have shown in this tire. So that's why I have not listed them over here. Okay, so I hope now you know how to calculate stress that is induced due to weight of the liquid on all the trays that are lying within this distance. Again, you have to remember this. So this stress is due to weight of liquid on all the trays that will be lying within this distance, the distance that we have considered for our analysis. Okay, so I hope this is clear to you. If you have any questions, you please mention them in the comment section. Okay. Then continuing our discussion with dead loads. The other dead load that will come into picture is weight of all the attachments. So for that, again I will show you a simple schematic, and you can see various attachment over here. So you have vapor outlet, manhole, railing, ladder, platform. All these are attachments. So you also have to consider the stress that will be induced due to weight of these attachments. Again, for our analysis, we are going to consider a distance of x from the top. So what are the attachments? You have trays. Now in the previous discussion we considered weight of the liquid. Now over here we are considering weight of trays, then weight of downcomers, weirs, overhead condenser. So all these are attachments, top head, all these are attachments, and you need to consider weight of all these attachments. That will be also one of the dead loads. Then platforms, ladders. So all these are attachments, and you have to consider their weights for your analysis. Okay. The total weight of the attachment will be in then in my discussion I have considered 6 types of attachments, 6 or 7 types. So accordingly, total weight of that attachments will be W1 plus W2 plus W3, addition of all the weights. Again, you please note these are weights having units of Newton. Okay. Then once you know what is the total weight, you can find stress due to that total weight by using this equation. It will be simply Fc80 is equal to W80 upon pi into di plus ts into ts. Again, di is the internal diameter, ts is thickness of the shell. Okay. So the point is you have to take into account all the attachments. You have to add weights of all those attachments. That will give you total weight of attachments, and when you know the total weight of attachments, you can calculate the stress induced due to those attachments by using this equation. Okay, so I hope this is clear to you. Now summing up all the dead loads, total stress due to all dead loads, let us denote it as FDL. So FDL will be equal to FCS, stress due to weight of the cell, plus FCN, stress due to weight of the insulation, plus FCl, stress due to the weight of the liquid, plus FAT, stress due to weight of the attachments. Okay. So FCS, you have this equation. I have already shown this equation. Then FCIN is given by this equation. FCl is given by this equation. I have already discussed about this equations. And then FCAT, that is FCAT, please, FCAT, the notation. So FCAT is given by this equation. Okay. So your analysis for dead loads will stop over here after considering stresses due to all dead loads, and you get a total stress due to dead load. So you need to calculate this. Okay. So now let us continue. That was about dead loads. Now you also have to consider stresses that may be induced due to wind loads, and in this case the column will be, I'm showing you a schematic diagram where you can see the action of wind on a typical column. So you have a column whose height is h, outer diameter is do, and if the height of the column is more than 20 meter, then you have to consider for analysis of wind load, for analysis of stresses due to wind load, the column has to be considered in 2 parts. So up to a height of 20 meter, you have one part, and the remaining height will be considered as a second part. Again, I have made a separate video. I have already shared with you. You please watch that. A separate video on stresses due to wind load. I have it is there. You can watch it. So in this case, stress due to wind load is given by this equation. I'm over here. I'm showing you the final equation. So if you want to go into details, you please watch my video on this topic. So FWB is equal to 4 into K1 into K2 into PW into x squared into DO divided by 2 into pi into di plus ts into ts into di. Sorry. What are the terms? K1 is a constant which will be having a value of 1.4 for flat plates, and it will have a value of 0.7 for cylindrical surfaces. So for tall column, you'll have cylindrical surface, and in that case you have to use K1 as 0.7. Then K2 is 1. K2 value of K2 depends on period of vibration. I'll talk about it. So period of vibration, if period of vibration is less than equal to 0.5, then K2 can be taken as 1. But if it is 2, if the period of vibration is greater than 0.5, then K2 has to be taken as 2. Okay, so for deciding the value of K2, first you need to calculate period of vibration and check whether it is less than or equal to 0.5 or greater than 0.5. So that need to be analyzed. DO is outer diameter, I have shown over here. DI is internal diameter. TS is thickness. Now these are very familiar terms. DO outer diameter, DI inner diameter, TS the shell thickness. Okay. As I said, we need to calculate period of vibration here for deciding the value of K2, and that period of vibration is given by this equation. POV is equal to 6.35 into 10 to the power minus 5 into H upon DI plus TS raised to 3 by 2 into W by TS raised to 1 by 2. What are the terms involved in this equation? H is the height of the column, W is weight of the column, but for using this equation, this weight has to be in kilonewton. You have to remember this. If you are using this equation for calculating period of vibration, then W, which is weight of the column, has to be kept in kilonewton. So you have to remember this. Then PW in this equation, it is given by this equation. Wind load, it is 0.05 into V max square. What is V max? V max is the maximum wind velocity in that particular area where the column is to be erected. Maximum wind velocity under worst conditions, worst weather conditions. And for using this equation, this velocity has to be used in kilometer per hour. You have to stick to this unit. Okay, so PW you can calculate using this equation. Okay, so this is how you can calculate stress that is induced due to wind load. Now let us talk about stress due to eccentric loads. Again, I have a separate video for this. You can watch it. Eccentric loads are the weights of externally attached equipment and parts. So again, if you look at this column, what are externally attached equipment and parts? You have ladders, you have pipes, you have manholes, you have overhead and side condensers, platforms. Okay, so these are all examples of externally attached equipment, and this may be responsible for, or this may be acting as eccentric loads. So what is eccentric load? For that we need to understand eccentricity. So if you consider load W, then its eccentricity is nothing but distance between the column axis and the line of action of W. So if you try to understand it with the help of this diagram, so if you have this you can say component, this is the central axis, and if W is acting over here, and this will be the line of action of W, then distance between this axis and the line of action is nothing but eccentricity for this load. Okay, so in this way you can find out the eccentricity. The stress is given. Now stress due to all those eccentric loads, it is given by this equation. FBE is equal to 4 into summation of ME divided by pi into DI plus TS into TS into DI, where summation ME is you can say addition of all the moments due to eccentric loads. So how they are calculated? For example, for W1 it will be W1 into E1. For W2 it will be W2 into E2, and accordingly for all the other loads. So E1, E2, E3, they are corresponding eccentricity. What is eccentricity? You can understand from this diagram. Okay. Stress that will be induced due to eccentric loads can be calculated by using this equation. Again, di is the inner diameter, do is the outer diameter, ts is the thickness. In the terms, you already know those terms. Okay. Then stress due to seismic forces. Again, I have a separate video. We can watch it. So for this, I'm showing you a simple schematic column, and again we are going to consider the height. Let the height of the column be h. The seismic forces will be acting in this way. It will be triangular pattern where apex is at the base of the column. Okay. So seismic load is given by this equation. Fs is equal to Cs into W, where Cs is the seismic coefficient and W is weight of the column. Again, it could be in Newton or it could be in kilonewton. Here there is no such restriction. The center of action of Fs is located at 2 by 3 times of the height of the column. That means the center of action of this load given by this equation, it will be located at a distance of 2 by 3 times of height of the column. Okay. Again, if you consider a distance of x from the top, then under the influence of Fs, seismic load, bending moment will be produced at plane x, plane at a distance of x from the top, and this will be given by this equation. Ms is equal to Cs into W into x squared into 3h minus x upon 3h squared, where h is height of the column. Okay. And then bending moment will induce bending stress, that will be given by this equation. Fbs is equal to 4 into ms divided by pi into di plus ts into di, where ms, we just saw that equation. Ms is Cs into W into x square into 3h minus x upon 3h square. Okay. So if you use this equation, you get the final equation for the bending stress. Fbs is equal to 4 into Cs into Ws. Ws, there is Ws is nothing but weight of the column. It is not Ws, it is W. So 4 into Cs into W into x square into 3h minus x into 3 into pi into di plus ts into di into h square. So if you combine these two equations, you get the final equation for stress that will be induced due to seismic forces. Again, di is the internal diameter, ts is the thickness of the shell. Okay. So under the influence of seismic forces, whatever bending stress that will be induced, it will be given by this equation. Okay. Now after we have understood all the stresses, that is stresses due to all types of loads, now we need to calculate combined axial stresses. Now circumferential stress that will be induced, that is induced due to pressures, we are not going to consider. We are just going to consider axial stresses, and using those stresses we are going to get combined axial stress. So how to get that, let us understand. So for getting this, first thing is we are going to assume that stress due to wind and seismic loads, they will not occur simultaneously. So this is the assumption. Wind and earthquake will not be acting at the same time. So this is our assumption. What is done? The maximum value of either is used to evaluate combined stress. So you calculate stress due to wind load, you calculate stress due to seismic load, and use the maximum of these two. The maximum value of either is used to evaluate the combined stress. Stresses due to eccentric loads, you may neglect it. You can neglect it. Rather, I have neglected in the analysis, and it is not a big deal if you neglect those unless eccentric loads are sufficiently high. You can neglect those things. Okay, so again, one more concept I would like to tell you. So if you have a column and wind is blowing in this direction, so this will be upwind side. This side will be upwind side, and on this side stress will be tensile stress. The combined stress will be tensile stress, whereas this side will be downwind side, and on this side the stress will be compressive. Okay, so you need to know, on the upwind side you have tensile stress, and on the downwind side you have compressive stress. uh, if you have this thing, that means if you have to find combined axial stress for this condition, that is for internal pressure and upwind side, then Ft max, the combined stress tensile, on the upwind side, nature of the stress will be tensile, so that's why it is Ft max will be given as Fwb or Fsb. That is, you need to consider either stress due to wind load or stress due to seismic load. The point is, maximum out of this will be considered over here. So that's why Ft max is equal to Fwb or Fsb plus Fa minus Fdl. What is Fa? Fa is stress due to internal pressure. What is Fdl? Fdl is stress due to dead load. Okay, then for this particular combination, external pressure and upwind side, how to get the maximum tensile stress? It will be given as Ft max is equal to Fwb or Fsb, maximum out of this two, minus Fa minus Fdl. That is minus stress due to internal pressure minus stress due to dead load. Then for this combination, internal pressure and downwind side. Now on the downwind side, stress will be compressive, and the maximum combined stress will be Fc max is equal to Fwb or Fsb minus Fa plus Fdl. So wind pressure, stress due to wind load or seismic load minus stress due to internal pressure plus stress due to dead load. And for this combination, that is external pressure and downwind side, the maximum compressive stress will be given by this equation. So Fwb or Fsb, one at a time, the maximum one, plus Fa plus Fdl, stress due to pressure, external pressure, and stress due to the dead load. So in this way you have to do the analysis. Okay, so now I have discussed how you can find combined axial stress. It could be tensile, it could be compressive. It is tensile on upwind side and it is compressive on the downwind side. And I have already, for different combinations, how to calculate the combined stress. Now you know. Okay, now let us talk about the design considerations. For safe design, the combined axial stress on the upwind side, that is tensile stress, FT max, it should meet the following design criteria. What is the criteria? FT max should be less than equal to J into F, where F is the permissible stress for the material and J is weld joint efficiency factor. So if you are doing analysis using combined axial stress on upwind side, then this will be the design criteria. The combined axial stress on downwind side, that is compressive, it should meet the following design criteria. What is the design criteria? FC max should be less than 0.125 into E into TS upon DO, where E is modulus of elasticity for the material, TS is thickness of the material, and DO is outer diameter. So for the compressive stress on downwind side and tensile stress on upwind side, you have two different design criteria. So if you are analyzing for tensile stress, you need to use it. You have to find, for the selected thickness, this should be the case. And for compressive down on or on the downwind side, this should be the design criteria. Okay, now thickness at the top, what are the steps, how to calculate shell thickness at different heights? So first thing that you are going to do is, thickness at the top is determined on the basis of circumferential stress, which is given by this equation. You already know this equation. TS is equal to PD into DI upon 2FJ minus PD, where PD is design pressure, DI is internal diameter, F is the allowable stress, J is the weld joint efficiency factor, and the thickness that you are going to calculate by using this formula, it is satisfactory up to a height of X from the top, considering X that we have already. So below X, if this is not satisfactory, if the design criteria is not met within this distance, you need to increase thickness below this height. Are you understanding it? So if you use you first, you are going to find out the value of X for the calculated thickness based on the design criteria which I have just talked about. In my next video, I'll be discussing a numerical based on calculation of thickness, so you'll understand that concept over there. So for time being, what we are going to do, first we will be calculating thickness at the top by using this formula. Then for the selected height of X, this thickness will be satisfactory. That means up to X, the design criteria will be satisfied, and the design criteria that I just talked about. But below X, you need to increase the thickness. Thickness has to be increased. Thickness will be increased beyond this thickness. A section of different height is selected below X. So again, you have to repeat the analysis. So when you start with X, you calculate all the stresses. You calculate the combined stress. You calculate combined stress on upwind side. You calculate combined stress on downwind side. Use the design criteria for upwind side, design criteria for downwind side, and get the value of X. Now, if X that you get covers the entire height of the column, there is no need of further analysis. You can use the same thickness for the entire height. But if this X does not cover the entire height, then you have to again consider a different section and repeat the analysis. A similar stress analysis is done for the selected section. Okay, so with the new thickness, you are going to do similar stress analysis. Okay, so this is to be repeated till the entire height of the column is covered. But most of the time, it will be done in the first step itself. There will be no need of considering a separate section. Okay, in this way, you have to get thickness at different heights, thickness of shell at different heights. So with this, I hope you have understood what I have discussed in this video. If you have any doubts, you please mention those in the description section. For now, thank you for being with me. Thank you for watching my video. Thanks for watching my video. Do subscribe to my channel. Tell your friends to subscribe to my channel. Hit the bell icon so that you'll be notified as soon as I upload any new video. Have a nice day. Bye bye. We will meet. See you soon in the next video.